What's up guys, today we're going to talk about my transmission of choice as well as make the parts to mate that to the 13B and touch a little bit on pulling geometry off of 3D scans. One of the more common questions that I got after my first introductory video about my swap was why not use the factory transmission? It's already in the car, it's already integrated with the electronics, should be nice and easy, right? Well, the power handling capability just sucks. Even in stock form, BMW recognizes this and they limit the number of launch control instances to 100. So after you engage launch control and launch the car 100 times, that feature is then disabled. So if we're gonna go and attach a motor to it that effectively on the low end doubles the factory output, then we're just asking for trouble. It's not gonna be worth the effort. If you caught my previous video where I talked about some of the control strategies on the car, I talked about FlexRay, and interestingly, out of all the powertrain components, the transmission controller was the only one that isn't on the FlexRay bus. It's purely on the CAN bus. So spoofing that is going to be a relatively easy task, and we can completely get rid of that. We don't need to keep the factory transmission controller in the car, which is going to simplify things tremendously. The same can't be said about the engine controller, but that's not today's problem. Most of the 3D scans used on this project were done myself with a Shining 3D Einstar, but very early on in the project, I needed to determine the feasibility of what will actually fit in the car. And to do that, I needed to rely on some third-party models and scans. So I ended up buying a 3D scan of the DQ500 from DomiWorks, I'm not really sure how you pronounce them. They're a European manufacturer of engine adapter plates. They do a lot of 8HP stuff, but they had a 3D scan for sale of the DQ500, which was a really attractive option as a gearbox because it was a 7-speed DSG that comes in the Audi RS3, and it's been demonstrated to have a ton of power handling, and anything that I'm going to throw at it should be well within the range of the stock transmission. And then if I need to upgrade, I can still upgrade the clutches after the fact. There's also a convenience aspect of choosing this transmission, as the ECU Master Pro 16 that I'm using to drive the 13B will fully control this transmission over CAN bus, so it's pretty much plug and play. There is a downside to this, however, because the CAN bus control is only compatible with the early model mechatronics, and these were only sold in Europe. So I had to make the decision of whether I buy a questionable transmission that's a little bit older out of Europe and pay for the freight into the US, or buy a more modern MQB series at DQ500 out of a US spec RS3 and then swap the mechatronics. I chose to opt for a US spec car that got a little bit too spicy at one point in its life, and I'm gonna have to go through and source a early model mechatronics. This is actually proving to be a little bit more difficult than I anticipated, as you don't typically find used mechatronics available for sale on eBay and the usual outlets. The earlier OBH mechatronics are available through a number of Chinese sellers of remanufactured units, but I'd rather use an OEM part if I can, so I'm undecided on whether I'm actually going to go down that route. If anybody has any leads on how to get a hold of an earlier mechatronics as well as the input shaft speed sensor, I'd love to hear about it in the comments, so drop me a line there. Dealing with the mechatronics is going to be a problem for future me, and we can do that after it's already assembled onto the motor, so not really a big deal there. I also briefly thought about a DQ250, but then I would have to go buy one and scan one myself, and by the time you upgrade the clutches to match the power handling of the DQ500, then it's kind of a wash as far as cost is concerned, and then you're at the limit of breaking hard parts instead of with the DQ500. You could then upgrade the clutches for even greater power handling. The positive with the 3D scan that they were selling is it was done with a professional tool. I think they use a Creaform or something like that, but the downside is that it was a $400 STL. That might seem like a big investment, but when you're planning a project of this scale, it was a reasonable upfront cost to not actually have to buy anything, and the DQ500 was probably going to be my transmission of choice regardless of what engine was attached to it. At that point, I hadn't yet settled on a 13B. It could have been a K swap, could have been some sort of compact V6. The options were pretty much limitless. Using the purchased 3D scan worked out really well for most of the design process, but there were a couple gotchas. The first of which was the bell housing was actually slightly modified. It had an ear cutoff, which wasn't an issue for me because that bolt would have interfered with one of the bolts for the 13B rear iron housing, and I was using that for my adapter plate, so no loss there. The second issue was slightly more problematic, as the factory transmission cooler was omitted from the scan, and I designed my airbox in such a way that the base interfered with the coolant hoses that fed that cooler. But today's sponsor, JLC 3DP, was able to provide me with a solution that enabled me to get a revised part without the pain and suffering of 3D printing it myself. JLC 3DP offers some 3D printing services in resins, SLS nylon, and stainless steel. I have used their services in the past for some smaller electronics enclosures and did some various resins and was really happy with the result, so I decided to give them a try for a larger object on my automotive project. This case, I chose SLS nylon for the material. The quality of the part was really great and all the dimensions were really accurate, especially for the holes for the press fit expanding knurled inserts for the threaded fasteners. Turnaround time was also really quick, in about 3 days. And of course, nylon is well suited to automotive parts because of its heat resistance and inherent strength. If you want to try JLC 3DP services on your own, check out the discount code and the link in the description and you can save a few bucks on those parts. Since there were some additional features present on the actual transmission after I received it, I went through and 3D scanned a portion of it to line that with the DomiWorks scan that I've been using up to this point. Now I can account for the transmission cooler and verify that I actually didn't need that extra ear that's on the transmission. All right, now that we have our appropriate scans, let's take a look in Fusion 360, or I think they're just calling it Fusion now, but I'll probably never stop calling it Fusion 360. Here we have the $400 STL from our friends at DomiWorks. It is actually a really high quality scan, especially in the details. If you look at the edges of the holes, they're much more crisp than some of the stuff with the Einstar, and that's pretty typical. There's definitely a performance gap in the price points on these. The Einstar is anywhere from $750 to $1,000 depending on when and where you buy it, and a lot of the professional stuff starts at about $5,000 plus. Having a 3D scan in and of itself isn't really going to do you much good. You need to be able to pull the geometry off of this, and this is where a lot of people might stumble. It might be tempting to directly convert the mesh into a solid model with the Convert Mesh tool. This is almost never a good idea. I don't think I've ever had any success with that tool in any capacity. But instead, what we're going to do is make a number of reference planes off of the mesh and then use mesh section sketches to get our geometry. So I'm going to do one quick example with the bell housing mounting flange, and every single dimension that you pull off of an STL is pretty much going to follow this process. So the first thing we need to do is go into direct edit mode, click your body, okay, and you're going to create a construction plane, and you're going to make a plane through 3 points. And since this is a high quality scan, we have a nice flat face here. What we're going to do is pick 1, 2, 3, and that's pretty good. See, we have a little bit of the mesh poking through on parts of the plane, probably sitting a little bit under on others. That's perfectly fine. Then we're going to do a create mesh section sketch. Click on the body, and we're going to click on the plane, and you can start to see what's going to happen here. We're going to want to offset the distance of the plane by a small amount. I usually start at 0.5 millimeters. That was in the wrong directions. We need to go negative. And now you can see why we did that. Now you have a sketch representation of the bolt pattern for the transmission. So let's get rid of our mesh. Let's get rid of our plane. We're only left with the sketch. You're going to want to right click that and edit the sketch. And then what you're going to do is go to Fit Curves to Mesh Section. Click your circle tool, enter, and then you're going to go through and keep doing that. Now the circle tool isn't always perfect. Like here, you can see it's picking up off some random stuff. It's picking up off all the center lines of the other bolts, which is kind of weird. But what you can do is click arc, click on that, and then that will give you the center point of this circular shape. And then you can make a normal circle, use that as your reference, go out to there, and then you start building out the rest of the bell housing. We'll do one more example where we can do a line. So basically what you do is you go through and trace out your mesh section sketch all your straight lines, all your circles, all the easy stuff, and then you can get a very accurate representation of what you scanned. So if we want to get a quick idea on how repeatable the dimensions are within the scan, I believe this hole and this hole should be for dowel pins, and they should be the same size. So let's put a dimension on that to see what the mesh was. All right, so we got 17.673 millimeters, 17.766. So we basically have about 0.1 millimeters of deviation. These are machine holes, so they should be pretty accurate in real life in comparison to each other. After you get all the dimensions that you want, you can hide the mesh section sketch. You can bring your body back into play, and then you can go through and start creating solid parts off of this. And I won't go through and do all the dimensions. As I said, this is the same process that you're going to use for everything. You can use that same construction plane, and then you can offset this. You can say constructs, offset plane, and then you can use that as a reference to get other dimensions off of, because in the case of a part like this face is really going to be the most critical part. So everything is going to reference off of that. Everything needs to be parallel to that, and that's a good baseline. Whenever you're reverse engineering anything off of a mesh, you're probably going to want to use the first plane off of the most critical part and then build everything else off of that. That's enough about pulling dimensions off of a scan. Let's look at my motor assembly and the adapter plate and all that good stuff. So we could jump over to the complete assembly model, and I also got the STL of the dual mass flywheel from DomiWorks, and in typical Volkswagen Audi fashion, this flywheel is different than the one in the US spec RS3 by a significant dimension. If you'll see on the side, the flywheel is shoved into the case of an interference situation. Right now it's actually spaced out where it should be in relation to the end of the crank, roughly speaking. This was another pitfall of using a third-party scan with parts that you don't have. You need to rely on these as best you can, and this actually resulted in me designing my original motor plate to be about 1.25 inches in overall length rather than a solid 1 inch that I'm at now. Also notable that I had to change the bolt pattern on my crankshaft adapter because this bolt pattern is different than the one on the US spec RS3. Way to go, Audi. So let's just jump right into bringing all the adapter plate pieces into view. You can see here how I adapted the dual mass flywheel to the counterweight on the E-shaft on the 13B. It's basically just a spacer. There's a big hogged out section here to account for the nuts on the end of the E-shaft, which is pretty big. This diameter here picks up off of a male pilot feature on the counterweight, and then that same adapter aligns with the snout of the input shaft on the transmission. And also notable that the reason that I chose to use the dual mass flywheel is that you'll see on a lot of transmission adapter setups, they will sell a sprung plate that looks kind of like a clutch disc, and you never want to directly couple the transmission to the engine. That's going to create for a very harsh and jerky experience. Aftermarket solutions probably do a pretty good job of damping those transient throttle situations, but the OEM dual mass flywheel is going to be significantly smoother and a much nicer ride and enjoyable experience overall. To create the adapter plate itself, basically all we did was project the bell housing geometry to a sketch plane, and then we did the same with the 13B. Basically projected this bolt pattern onto that same sketch plane, and then we basically just filled in the blanks and made a bunch of fillets to create a final shape that covered all of the bolts from the bell housing as well as the motor rear housing itself. Rotating to this side, you can see where there's provision to mount the starter on the side here. One of the nice things with the DQ500 is that the starter is mounted to the transmission. So in the event that my high voltage starter generator on the main hybrid system is in a fault state, I have a backup so I don't have to wait on the side of the road for AAA to show up. But I'm sure that's going to be a situation that I'm going to have to deal with a number of times for various other faults as well. On the subject of the Audi starter, one thing I did have to take a guess at was the spacing of the dual mass flywheel. I wasn't able to get a good reference dimension on what that should be. However, all my initial measurements, the flywheel clears the starter when it's not engaged, and when the starter is at its full stroke, it should have good engagement of the pinion gear on the flywheel teeth. Ultimately, if we have to make some adjustments, the flywheel adapter will fit my lathe so I can turn it down, or if we need to space it out more, then that's just a simple matter of a shim spacer from Send Cut Send. I was a little bit nervous in using a 3D scan to design all this stuff because you have multiple bolt patterns that all have to align in a very accurate manner. And one of the ways that I did this was to create some solid reference bodies based off of the mesh data. So if we hide that, you can see where I created just a dummy cylinder for the spline of the dual mass flywheel, or rather the input shaft where it engages with the flywheel. And also have the pilot snout where it goes into the crankshaft, or rather E-shaft adapter flange. So in terms of design, it's a pretty simple part. It's just a matter of getting all the holes to line up correctly. In order to bolt the adapter plate to the motor, we have some countersinks for the fasteners, so we have a nice flush surface for the transmission to mate up against. These are two 1/2-inch laser cut plates that are bolted together because this was a cheaper manufacturing option over getting it CNC cut out of one piece of aluminum. Order of assembly is pretty straightforward. You bolt the motor plate onto the back of the 13B. You bolt the crank adapter onto the back of the E-shaft. You bolt the dual mass flywheel to the adapter. And then finally, you install the transmission on top of that. We will still need to design some covers for these access areas, but that's going to be an easy future project. So now with everything designed, we just need to hop on over to Send Cut Send, upload our files, and order some parts. The flywheel adapter is machined from 6061 T6 aluminum, and I sourced that through Parts Badger, which is a Wisconsin company, and their model isn't unlike Send Cut Send, where you upload your file and they give you a quote. They were able to turn this thing around in less than a week. All of the dimensions were dead nuts nominal to my model, and I was really happy with the final part. Everything fit really well. So fast forward about a week, and we've got our freshly cut and anodized plates from Send Cut Send. This is actually the first time that I have utilized their anodizing service, and this is really done for no other reason than aesthetic purposes. The raw aluminum would have been just fine, but I'm really happy with how this turned out. Looks great. As expected, all the holes and geometry lines up perfectly. There was, however, an unintended consequence of one of the selections that I made during the ordering process on this plate, where the plate bolts to the 13B, I used some flathead countersunk fasteners, and I thought I was doing myself a favor by getting the countersink started so I had less material to remove. Unfortunately, Send Cut Send doesn't offer a countersink big enough to accommodate this fastener head. When you get a hole tapped, such as this M6 fastener, what Send Cut Send will do is automatically resize the hole if your as designed hole does not properly line with the drill size for the tap. And I didn't realize that they do the same for the countersink. So this was supposed to be a 10.2 millimeter diameter hole, and then countersunk for this head. However, when I selected these holes to be countersunk, they were automatically resized for approximately an M8 fastener. So not the end of the world. We're gonna have to countersink these more anyway, but now we're gonna have to go and open up that with a drill, but lesson learned. So keep that in mind when you are ordering similar parts of your own. But the first step is to bolt both of these together. So you can see the issue that I was talking about here, where the hole in the gold plate is a little bit smaller. It should be the same diameter as the black plate. These are larger to accommodate for the dowel pins on the motor, so those are as they should be. Next up, we need to tap the lower 3 transmission bolts for a M10 by 1.25 thread. One side is already tapped via Send Cut Send, and then we're going to use that as a guide and then go through and finish tap the other side and everything will be aligned so we can have full 1-inch thread engagement of our fasteners. So because the holes are already started and we've got the countersink to guide the drill bit in, we're going to be in pretty good shape maintaining the accuracy of the bolt pattern. Now that we've got the holes open up to the correct size, we're just going to quickly go through and finish out the countersinks. Again, we want to make sure that we are well lubed so we don't gall up the metal. It cuts a little bit easier without chattering. That drops right over the dowel pins. We got no real play, everything's flat. All right, it tightens down, our fasteners are flush, everything lines up, so we're good to go. I used factory Audi dowel pins for the alignment. They were a little bit longer than I anticipated, so I had to take a little bit of material off. They could only go 12.7 millimeters max into the adapter plate, so we shortened them up a bit and everything clears now. Last step we gotta do on this is to press these alignment dowels into place. We already machined these down to the proper length. Should be a very close fit. We're gonna pop a couple fasteners in, and then we're gonna slide our E-shaft in and see how that spins, and then measure the end of it for run out to see how concentric we are with the rest of the assembly. So we have this set up here to verify how much run out we have at the end of the E-shaft. It's important to note that this is not going to be a valid means of measuring how straight our E-shaft is. You really need a set of V-blocks for it. But what this is going to do is serve as kind of a sanity check to make sure that there's no crazy misalignments and that everything turns easily and is concentric, because we have the stack up of the transmission input shaft, the flywheel adapter, plus the E-shaft, and then we also have some bearing clearance as well. The maximum allowable runout for the E-shaft itself is 0.06 millimeters. We're at about half of that right now, so this is all going to be good to go after it's assembled. The fact that we now can physically adapt the transmission to the 13B is a major physical step forward in this project, because this was the primary step that was holding me back from actually assembling the 13B into a complete finished motor. From there, we're going to be able to finish our mounts, get this thing bolted into the subframe, start building out a wiring harness and figuring out a lot of the smaller components, and get a little bit closer into firing this thing up. If you made it this far, thanks for watching, and we'll see you next time.